Hello.
Yes, hello, good evening everyone. So welcome you in this today's session. So now our speakers have joined. So yeah, Mahen sir, good evening.
Good evening,
Can
sir.
you
Good
hear
evening.
me?
Good afternoon. Good afternoon. चलिए करते हैं.
Yeah, just a minute.
चलो थोड़ा सुन के जाना. देखते हैं कुछ. Okay, so can we start now? Or maybe we can wait. Arvind sir? Okay, so
Just wait a minute, sir. So
okay.
yeah,
Okay.
good evening, sir. Mahen sir, can you hear me?
Yes, yes, sir. Yes, sir. You are audible.
Yeah. So
Yeah.
good evening everyone. So before going to start our session, so first I would like to introduce our speaker. So today's speaker is Dr. Mahent Kumar. He is working as an assistant professor in instrumentation and control engineering department and associate faculty at Center of Energy and Environment, Dr. B.R. Ambedkar National Institute of Technology, Jalandhar, Punjab, India. So before he has worked as an assistant professor, HOD, Biomedical Engineering Department and R&D coordinator at Faculty of Engineering and Technology, Datta Meghe Institute of Medical Science, deemed to be University, Sawangi Meghe, Wardha, India. He has completed PhD from the Department of Electrical Engineering, Indian Institute of Technology, Roorkee. In addition, he obtained MTech in Control and Instrumentation Engineering specialization and BTech in Electronics and Communication Engineering from State Government Rajasthan Technical University, Kota in 2012 and 10 respectively. He has around 8+ years of teaching experience and teaching and research experience. Besides, he was awarded by gold medal for excellence in MTech by Rajasthan Technical University, Kota. From research point of view, he has published research works in IEEE Transaction, IET, Taylor and Francis, Springer journals. His research area is to design next generation control, resilient control, reinforcement learning, cyber security, cyber physical system, and their applications in autonomous systems, microgrid, power system protection and control, DC to DC converter, EV, and agriculture. So now I would like to request Dr. Mahen sir to please share your screen and you can start sir your lecture. Sir, you can unmute your mic is muted. So can you unmute and then please speak? Mahan sir, your sound is muted. Can you unmute?
Okay. Now it's okay. Fine.
It's okay, sir.
Okay, sorry. So let's we can start. Okay, so like good evening to all delegates and organizing team members. Today we discuss about some robust control design, its application. Now, so I really thanks to organizing committee of the GRACE PS 2025, MNIT Allahabad and NIT Patna organizing team members. Now, this is a table of content which is we can discuss here. Like a little bit background about me, and sir is already introduced a lot of things about me. Told you, and something about we can go in the control perspective mainly, then application the power electronics power converters, power system for load frequency control, and some cyber physical the microgrid works. So and some RL based things, reinforcement learning based things for the control. So we can just check all the things. Okay. Now, so if someone want to maybe work with us, so we have currently some cybersecurity project, like 7 CR. So we have the 3 GRF recruitment and 1 RA. So anyone who maybe want to join us, they will join. I have worked with some another consultancy projects also, like some polyoptics and the cybersecurity work. Okay, publication, a lot of things you can go with the website and you can check, and somehow some patents also. So maybe you can check on the website also. Okay, who want to maybe work for discussion. So this is my research team. 5 PhDs ongoing, and the 3 MTech completed, one is ongoing. So they have like doing the some work in the control and application of electronics power systems, and like battery health monitoring like things. So this is the currently working things. Now a little bit background here, sir is discussed already. Like so these are some of the setups where I worked during my PhD, and currently I'm also working on the some setups also here at the NIT Jalandhar. So we have the some like embedded controllers, and some C2000 industry controllers, and we have the temperature kits, some power, we have the DAP converters here, some power supplies for there, and some load condition, like electronic loads. So and these are the some of things we are in the under purchase. Okay, so like motivation why we need to go with the control and maybe go for the a lot of things you heard about, like conventional control, robust control, resilient control, and today's next generation control, maybe AI based control, data driven control. Okay, and adaptive controls. Okay, so we first discussed of why we need to control, like in each and every system, whatever system you seen around you every day. In every moment you see some of the things which is have the some control, like some control things, and something which is related to control. Okay, so uh, you've seen the agriculture domain, biomedical domain, your missile guidance, aerospace, aeroplanes, and like my power system, smart grid, and whatever things you in process, chemical industry. Um, so everywhere you maybe need some controls, like things like whenever I speak, so you have heard, yeah, I'm properly audible or not. It is also one of the feedback which is you provide to me, and I will like maybe speed up or maybe the slower my talk. Okay, so this is also one of the, like, you are controlling me. Okay, based on your observations, and based on the your listening. Okay, so these are the some motivation which is need to maybe you work on the control. Okay, now so some of the key problems, issues, and solutions. So like every system we have some issues with the system. Okay, system is what the thing, there is some system which is have some input and we get the some output, but in between the system have the some key problems like external internal disturbance, noises, parametric uncertainty. System have the system, there are some parameters which may be the changes with the aging condition, or maybe the temperature, or due to the some another reasons. Non-linearities in system, cyber attacks. In the currently we are working with the AI domain, AI era. So there is a cyber attack issue. Time delay is also issue in the, we are working with the analog system, but we are, our processors or controllers have the digital. So in such a way we have some time delay issues due to the conversion from the like A to D to A, and time varying disturbance, stochastic nature of low demand, intermittent nature of the renewable. Like you are working in the renewable, or today's we are like in the environment friendly energy based things. Okay, we are not going with the conventional sources, so we are moving towards the renewable sources, and eco-friendly. So in such a way, we can say like renewable energy sources are the more needed, but they have the some stochastic nature, okay, or intermittent nature. So these are the some key problems with the system. But what are the key issues in the control design? Like stability, one of the things, fragility, robustness, resiliency, adaptivity, and intelligence. So these are the all parameters are not come with us togetherly, but somehow we can maybe capture some of the not one, maybe 2 to 3 properties togetherly. So one of the map is like available on the web, like so there is defined the from the map of control theory from initial one to like today's what data driven AI things. Okay, so you can maybe check on the website through this particular link. Now, so basically you heard about the PID. Everyone maybe the here who is present, they knows the PID controller. Okay, so PID controller, you know, it is a basic and initial controller which is maybe available in the like industrial things. And today's also 70% of the PID maybe controllers based on the PID, or in the industry like process industry, they have the maybe 90% times 90% of the controllers. Okay, so PID, why people are mostly work with the PID? The reason is that, you know, it is a simple design. Okay, and industry people also working on that from the last last duration. So they adapt, they know how to handle the PID controller. A lot of algorithms are available for how to tune and how to maybe the like think the parameters kpki kd. Okay, there is a 3 parameter kpki kd. So how do you can consider these values to get the your better response with the system. Okay, so based on the experience, industry people are doing with the manual control. Okay, manual control in the PID, they have the KPKI KD, they are like trial and error based thing, they are continuously changing and they get the responses. But it is not a like a one way of the automation. In automation, we need to KPKI KD values and we need to some tuning algorithm. So optimization people are prefer some analytical way and some AI concept will be coming up. Okay, now so what are the issues with the PID? Okay, no, so there is a last, it can't handle the last time delays which is available in this, then the system maybe go with the maybe not controlled properly. Time varying systems, there is one of the issue. Design higher order systems are complex because analytical design is available for the second order system. So PID is available mainly for the analytical process, or maybe the mathematical way we can go for the second order system. That's why we are use the reduced order modeling also. So in case of we have that 100 orders of the system, then we can convert maybe in the second order, first order system, or maybe we include the time delay. Okay, so then in such a way we can convert in the first and second order, and we can design our controller PID types controllers. Now, so and there is a one bigger things like in the PID is the tuning of the PID gains. Okay, gain coefficient like KPK, KD values. So how do we can design these things? Okay, and how do we can select the for non-linear system, autonomous system, power system? There we have the maybe 100,000 order of the order. Okay, now system orders. So you know, like KPKI KD, they have their individual issues also. So that's why we are combining the KPKI KD. But KD also have the issue of the noises. So if there is a noise in the system, then we need to design the derivative filter, or maybe design the KD in such a way there is a very less impact of the noises. KI is, you know, saturation issues. So you can go with the saturation integral things, or maybe you have the some special treatment with the KI. So you can handle the itself like issue of the KI KD, then you can enjoy with your PID controller. Now, so some of example we considered here, like we have considered one of the transfer function, like plant transfer function. It is okay. So we have the two poles at the at the origin. Okay, just like you observe from the equation 2. Okay, so here we can plot the root locus of this particular plant like equation 2. So we can go get the response here in figure 6, and we have the transfer function. We design some controller for this particular system to handle it and get the some desired response. But PID we design based on the some like reference 6 or 7, and we can get the PID just like the equation 3, and we can plot the loop gain loop transfer function of the for the like GS and GPID, and we can get the such response like equation figure 7. But here you can observe that somehow the system is not controlled and our response is not towards in the left hand side. Okay, so in such a condition PID not handle the type of the system. So in such a case some researchers have worked and they suggest that why not we can go with some another controller. It is a PIDA. It is basically like an extension of the PID. PIDA is nothing but proportional integral derivative acceleration, or acceleration one of the like we can say double derivative term. So in the literature, it is available like PID plus DD or maybe the PID2 type of controller. So PIDA is mainly introduced by the Jung and Robb in 1996. And there is a general theory, you know, that whenever we add some extra zeros, then the system stability and damping is improved. So based on this fundamental, they have improved the added the zero in the transfer function of the PID. So based on these things, we have the like mathematical expression of the PIDA is just like the equation 4, and we have the KA is one of the extra element here, which is we need to maybe the provide the more degree of freedom to select the controller. Okay, now so the following important points regarding PIDA controller are observed from the literature work, just like that. So there is a main attraction of the PIDA is the two derivative terms, and another condition, the PIDA control provides a more degree of freedom in the designing and also satisfy more design constraint or specifications of the control system in comparison to PID. So maybe it have the three, four design parameters. So maybe we have the more design constraint we can satisfy for the PIDA control design. Okay, so but we can't say the everywhere the PIDA is worked. But in case of the like we can say aerospace or space application, where is the derivative is more effective, then you go with the PIDA control type. Okay, now so we designed our PIDA based on the like 6 and 7, and for this particular plant equation 2, and we get the root locus like the loop transfer function, just like the figure 9. So from this one we can observe that the somehow a lot of like for the more some values there is a system not disturbed, but other values the system is go in the our under control. Okay, now so in this way the PIDA is effective in such type of the like double derivative type system, or not for double for the poles at the like at the origin, maybe two poles, three poles, then a little bit we can go with that. Okay, so two poles double derivative. If you go more, then you can extend the PIDA in the PID uh, PID DN. Okay, D1 D2 D3, so you can add like that. Okay, now so some of the like during the literature work we found that the very least algorithm is available for the PIDA control, like some algorithms of DOF approach, kitty method, coefficient diagram method, multiple retention of dominant pole methods. So every approach has their pro and cons, and based on that we have I have worked with this some CDM work, and it is a very easy algorithm. And I also worked with the IMC, which is not earlier discussed in the literature. Now so based on the application, also PIDA is applied for industrial and academic applications like servo motor, torsional resonance suppression, induction motor, and automatic AVR and low frequency control. In the earlier one before I done, but then I worked with the low frequency control and some servo motor control. Okay, now so here we discussed like coefficient diagram method, internal control method, and the optimization tuning approach. But I will also discuss with some RL perspective here. Okay, now so just a second, लेक्चर में मैं भी बात करता हूँ, ठीक है, आ रहा हूँ, मैंने कर रहा हूँ. So I discuss about some CDM robust coefficient diagram method. Then we can discuss the RCDF for the thermal and hydropower plant, and also the like we can say converter DC-DC buck converter. And also I designed the IMC with the PIDA control for the time delay system and microgrid system, and the thermal and hydro type system. You can also design it. Then we can go with some resident control for cyber physical microgrid system, reinforcement learning for the control design for the single area bus system. Okay, so importance of the LFC or AGC for the Indian power system. Like in the earlier 2018, we don't have any AGC or low frequency control in our Indian power system, but in 2018 they have started some pilot projects, and now somehow it is started in some power plant, but not in everywhere the AGC is installed. Okay, now so from introduction of CDM, it's like we can go with the CDM first, discuss, then we can its application. So first, what is the like CDM? Okay, so CDM basically introduced by the S. Manabe in 1998. People have worked earlier one, but the like particular mathematical formulation to for applied one, it is done by the Manabe in 1998. And CDM is basically nothing but the algebraic or polynomial control design approach. It has the some like characteristic equation thing. So it is also one of the polynomial you form. So in this way CDM is worked, okay, or easily. Okay, you can form the polynomials like denominator, numerator things, and you can just cross multiply things and you can get the some results, okay, in comparison of the two polynomials. So important feature of this control design approach is to simple design, set point tracking, and disturbance rejection capabilities. So characteristic ratios are the main design parameters here. So like gamma, I, and tau is to design constraint parameter, which is used in the CDM, and based on this parameter we can get the better transient response. Okay, so here CDM is what? Nothing but there is a polynomial transfer, like a polynomial approach or algebraic. So we consider the generalized transfer function of the any system you have, like equation 7, and always we know the AI and BIs is nothing but the real coefficient. N is always equal and greater than M. M is nothing but the order of the numerator, and N is nothing but the order of the denominator. So the transfer function of control is given like the equation 8. We consider here nth order transfer function also, but here we consider like Li or Kj is similar one to the A or Bj and real coefficient, and the here we form the like one of the target characteristic closed loop polynomial, just like the equation 9. P target is nothing but ds dcs plus ns, and ncs and dcs is nothing but the controller parameter polynomials, and ds and ns is nothing but the system transfer function polynomials like numerator and denominator. So basic objective here to maybe we need to know the unknown value of the controller, like the here k or l parameter, different KIs and KJ and LIs parameter. So and based on that, whatever we have the some overshoot and settling constant that, but in the controller whatever the function we consider in the equation 8, it is just like the nth order polynomial transfer function. But we in the controller generally like PID we have the integral parameter is needed because of steady state response to get the desired. So in such a case, we in equation 8 we can go with the L naught is the 0, so we can get the integral control effect also in the our controller design. So here we form the one of the desired characteristic closed loop characteristic polynomial like equation 8, and here we have the we need to design find the value of the pi. So by comparing equation 9 and 10, like equation 9 you can from the controller and system parameter, and 10 is you can get from the based on the selection of the characteristic ratio gammas and tau. So we can if we got the value, like select the proper value of gamma as tau, then we can frame the equation 10 and we can compare equation 9 or 10, then we can get the unknown parameters of the controller like PIDA or PID or whatever another polynomial controller you want to design. Now, so characteristic ratio is related with the like with the your characteristic equation polynomial coefficient like PIs. So this is one of the relation with the gammas and PI and the tau and PIs. Okay, now so this is one of the generalized formula for the tau time constant with the settling time, and you can consider the settling time whatever system you have based on the experience. You can select the TS, and PI you can calculate it in terms of the tau, gammas and tau. So tau you can calculate based on the settling time, choosing based on the settling time, and gammas you can select based on the some particular phenomenon trial or error method, and the some particular algorithm which is we will discuss in the coming slides. Okay, now so based on the this particular p naught or gammas like things pi we can get, and we have that this particular p desire is nothing but that in terms of the tau and gammas, and p naught you can consider maybe this one, some of times we have considered also one. So there is a like whatever the 14 you can get, but there we have the some certain like criteria how do we can select the gammas. Okay, here so gammas you can select based on the 14 and 15 and 16 some constant conditions, and if we satisfy these conditions, then we can say that this particular p desire is stable like characteristic polynomial. Okay, now so there is a like in the CDM what Manabe suggests that you can consider the gamma 1 is 2.5 or always gamma 2 and any other value of gammas maybe you can consider 2, then you can get your desire, but it is not possible. So in such a way the CRA one of the algorithm characteristic ratio assignment algorithm is introduced by the Kim, Kill and Bhattacharya in 2003, and this work is published in the IEEE in the tech IEEE tech, and this algorithm have the some like particular things that gamma 1 you can select that one based on your trial things and maybe some value, and you can go the other value gammas gamma 2 gamma n till np minus 1 based on the some particular formula. So what is the discussion of the CRA is coming in the next. So this is a like theorem 2 we discuss here. we consider one of the all pole closed loop transfer function like the GPS as equation 17, and here we consider the characteristic ratio gamma I, and we can select the like two conditions satisfied. If the two conditions like gamma 1 is always greater than 2 and gamma k just like the from the like point 2, we here we can see here. So then we can say that the GPJ omega is monotonically decreasing function. It means always go with this some stability condition proper, and QS is a Harvey stable polynomial. So you always go to your response maybe somehow some desired way. So what the gammas in the early Manabis say gamma 1 2.5 and the gamma case is 2 always. But here CRA they have the gamma 1 you can select greater than 2 and gamma k you can select based on the gamma 1, okay, based on the like this relation. So there is a one of, but there is a there is a one challenge selection of the gamma 1. So for this one I have suggest something like based on the maximum sensitivity and which is we called as the robust RCDM. Okay, now so firstly we can go with the some basic CRA based things and we can go for the RCDM. So here we design the like polynomial proposed polynomial control design based on the CRA. So here we consider general second order system like equation 18, and we have to consider second order polynomial control like that equation 19, and we have the one of the pre-filter transfer function like the equation 20. So we know we need to know the k2 k1 k0 l2 l1 or fgain values here. So these are the values we can calculate it by the analytical way for the reference proper reference tracking, disturbance rejection, and asymptotically stable system of the closed loop in the. So these are the values which is we derived in the mathematically, and we can get these values, and these are all the based on the system parameters mainly. Now so here we consider one of the example like the first order unstable system like the GS26, GS 1 by S minus 1 to minus 0.5 as. Here we apply the first order party approximation, then we can convert this particular delay terms in the particular polynomial numerator and denominator form, and we have the like we can observe that the system is unstable and the non-minimum behavior. So here we based on the like theorem 2 we can say gamma 1 2.5 and gamma 2 gamma 3 based on the equation, okay, this 0.2. So here we consider settling time like 3 seconds, so we got the tau nothing but 1.2 seconds. So based on these parameter we form the our controller and the pre-filter like equation 28 29. Then we designed our controller for the particular system like unstable equation 27. Then we get these some simulation results for step reference checking and the disturbance rejection. So in the both the way we compare with the some existing one, and we can go maybe we observe that from these figures like that the our design like polynomial control has some better response as compared to existing. But I can't see the from the here we observe that okay done it, but from the perspective of the like some quantitative way we got the something else or something maybe the challenging things which is we need to focus here. So from the integral like integral performance indices based reference checking we can get the better one response from here, okay. But somehow some Janka and Pade have the less control energy, like C is nothing control energy which is we capture. So polygon is get the more control energy, maybe require more control energy. It means for the reference tracking we need to more control act as compared to Janka and Pade and Maji because they are the PI based controllers, okay. Now but in case of table 2 we are performing similar way for the disturbance rejection, and from here we observe that the for the quantitative way, okay, for integral performance it's okay, but C also is a good way and less control energy in the mitigation the disturbance effect, okay, on the system. So in such a way we can say that the for disturbance perspective the polygon is more better as compared to existing, but in case of the referencing it is good, but for control energy it is a little bit it requires the more energy, okay. So from the maximum sensitivity concept also we have considered like polygon and like Janka and Pade have the in the similar range which is we consider based on the delay, and from the all the quantitative and the graphical or maybe the graphical analysis we observed that the polygon is have the better response as compared to other controllers, and you can apply this generalized controller for any type of the application and select the gammas in better way like based on satisfy the constraint stability constraint. Then you can get the maybe the good results, okay, for any type of the unstable stable integral type of the systems, okay. Now so next we go with the some hardware way. Now so we consider DC buck converter here. Now so why we maybe go for the DC converter or maybe converter time, inverter and converters you always heard about some DC to DC, DC to AC, AC DC DC, or sometimes this type of the cyclo converters, inverters, rectifier, all the things. Why these things are required? Because we are going with the modernize ourselves. Okay, we are mainly go with some power electronics dependent things. Okay, so power electronics things, there is some issues with the converters, like the in the basically DC converter, in the buck converter we have the load condition. If the load is changed suddenly, then it have the voltage control is a little bit tough things. Okay, now so these are buck converter is highly sensitive to sudden change in the load, and major issue of the output voltage control is in buck is addressed here. So we can go with the tracking of the output voltage, while the some some disturbances or some load disturbances, another condition. Okay, now so this is one of the non-ideal buck converter, which is actually designed by one during PhD my one of the senior Vishnu and Siddhartha. So he worked on the hardware. I just tested my controller, but we got the results in better one. We can publish the one of the transition on the same work. Now, so this is a structure. Why we are going with the non-ideal? Due to these are the our own. These are the extra loads. Okay, RL, RD, RC. These are the non-ideality of the buck converter. If you have the ideal buck converter, then you are just remove these things. Okay. Now, so these are the some parameters which is considered for the designing perspective. Input voltage is from 12 to 15, and then we have the our output voltage 8 volt. So it is buck because we have the higher input and output less, and we have the like load resistance 10 to 20 ohm. We change it. Okay, now so this is one of the non-ideal DC buck converter transfer function, and based on these values we get the something like transfer function is 31, and we designed our polygon controller like gamma 1, gamma 2 based gamma 3 values we select based on the CRA algorithm, and we have the TS is selected here the 2 milliseconds. So tau is nothing but 18 × minus 4 seconds, and based on these parameters we have the polygon and the pre-filter transfer function. Okay, so here we go with the regulatory control problem like servo problem, no disturbance rejection problem, and the servo control like reference tracking problem we reference. So here we consider the 8 different cases study, like nominal condition. There we have the reference 8 and our input voltage 12. Cases 2, there's sudden change in input voltage, and third is the sudden change in reference, sudden change in load, and the some uncertainty in the inductor and capacitor. These are certain 10%, 20% plus minus is considered based on the tolerance perspective. Okay, now so this is a nominal condition. Here we consider like we can get the 8 volt as the output, and but if we have the different reference tracking, then we can get the also similar response as compared to better one IMC PID. Now, so from the simulation and experimental way, we can go with the experimental results also. So based on that polygon have the less rise time, or in such a way we can get the some better response as compared to IMC PID. Now, so these are the TV is not total variance. Yeah, it is better way to whenever you work with the controller, then you can go with the control energy or maybe the total time variance or total variance. So in such a way you can check your controller is effective or not. Sometimes what if we design the controller, it bears a lot of energy, and we said that it worked for system, it is not. It is not too good. So you can always, if you work in the control, then you can go with the CE or maybe total variance. So do it. Okay, and MS is for the stability perspective. Maybe you can trade off between the stability and the performance. So MS always provide the better response to you. So MS for general system 1.222. For any stable system you can go, or if you go towards the 2, then you have the performance better but the stability is less, and you can go towards the 1.2 or maybe the below 1, then the system is more stable but the performance somehow the lack. Okay, so we change the input voltage here, like from 12 to 11 and 11 to 12, and from 12 to 13, 13 to 12, in such a way that our reference is not changed much more. Now in case of the reference change, we changed here, so reference properly take the our changing in the reference voltage. Now for the sudden change in the load, so here we definitely we check, but with the IMC, in compared to IMC, there is a very less fluctuation in the voltage. Now if you plus minus 10% parameter considered in the inductor and the capacitor, in minus 10 plus 10 we can get the better response as compared to other one, and there is a very less overshoot and like things in similar way for capacitance also, and there is a similar perspective. Okay, now so from the hardware perspective also we can go with that. Some simulation results, so hardware results. So this is I thought we take from here, but there is a rise time 600 microsecond. Now in the another way where we change the input supply, but our not change in the output voltage much more. Now the here is for reference, it track the properly, and for the load is also have the track again. We choose the from load, then we can get our proper output at volt. Now, so from the above we summarize that the very small or should understood with the in the output transient response and trade-off between the robustness and performance for all stable and unstable system. Like we can mitigate the disturbances also, and we have the better disturbance rejection capability, require less control energy and to improve the aging and the efficiency of the hardware control. If the controller is more bugged, so then there is a age issues or maybe the zigzag issues also, and maybe have the issues like the from like aging. So or if there is some hardware, then jig is the issue. So very small values of the integral, so as so the better performance. Now, so we can go with the RCDM. Okay, so RCDM is nothing more towards like like towards have the like some like some different work, but it is incremental work. But here is one of the things, like we select the gamma 1 is based on the maximum it is one of the one unique things which is involved, and we get the better response. Okay, now so here we work with the thermal hydropower plants. Okay, now so ms is nothing but the inverse of the sorted distance between the critical point and the next point at the point c. So this is one of the graphical interpretation of ms. So this is your unit cycle. Okay, this is your unit cycle, like, okay, now, and this is your plot of the plant. Then it is a distance between the both, okay, unit cycle and the like this particular system plot. Okay, now so based on the ms is nothing but the is just relative, and maybe that we can say the related with the gain margin, phase margin. So in the like in the literature, people are working, select the gamma gain margin, phase margin values and select these values and choose the design the control. But here ms is one of the single sufficient parameter which is design, we can design the controller and maybe handle the gain margin and phase margin, both the properties. Okay, now so here we can go with the like a relationship between the gain margin, phase margin through the equation 34 35, and there is some certain condition you can think from here, like whatever I discussed in the earlier one, ms is 2, then we have the your gain margin like 6 dB or maybe the phase margin less. Okay, but you if you have the ms 1.2, then you have the phase margin or am like gain margin is have the 15. So in case of the like gain margin and phase margin positive towards the high value, then we can say the system is more stable, and maybe less values, then we can say the less stable. So this is a fundamental we can observe from here. Now, so how do we can select the gamma is in terms of the ms? So here we can select the like one of the mathematical expression of ms, like maximum of omega, or maybe limit omega tends to infinity and 1/1 plus lg omega. So you can put the values of lg omega, and we can have the relationship like the ms in such a way in terms of the unknown values of the controller. Okay, so we select the some values here in terms of gamma tau and the coefficient from the calculation, and here we always have the relation like ms and gamma. So some of the values we select here, and we can go with some curve fitting approach, and we can have the relation like 40, equation 40. So gamma is in terms of the ms. So whatever value of the ms you can select, gamma is design, and you can design your controller. Okay, so these are some steps which is we follow for that. So we apply here for load frequency application. While load frequency control is very much required in today's scenario or in future, because we are integrating the renewable in the our conventional power system or in power grid. Okay, so how do we can handle this intermittent nature of the renewable? So there is a frequency is continuously fluctuating, and such a way we need to control our frequency at the 50 hertz or maybe within the specified pre-specified limit of the frequency limits. Okay, so frequency we need to be because there is some load disturbance capacity out is the frequency maybe changes, so maybe sometime up or down. So here we consider single area power system load frequency control dynamic, like figure 25, and we have the gj is nothing governor transfer function, gt is turbine transfer function like dynamics, and gp is another power plant and load dynamics. Okay, so r is nothing but true. So this is the primary part. Without the cs we have the primary part, primary frequency control, and if you consider the cs, then it is called the loss frequency control, secondary frequency control. Okay, so del f is nothing but the deviation in the frequency, del pd is nothing but the deviation in the like it is a disturbances or maybe the load changing. Okay, now so here our main approach is to design the cs. Okay, so there is a one condition we need to satisfy, like the limit t tends to infinity del ft, maybe at the like t times t tends to infinity, then the frequency variation is 0, okay, from the final value from the Laplace. Okay, so here we consider that the bounded changes or bounded function of the del PD, because we can't go with the uncertain or stochastic way, or maybe there's some if there is not bounded unbounded things we can't consider for the del PD, then we can't handle the things from here. Okay, now so we got this one of the transfer function for single area power system like equation 41, and we have the some different transfer function GG, GT, and the GP, and we have the hydro turbine here also. The hydro turbine have the non-minimum phase behavior due to this particular, you can observe from this transfer function also, because zeros go towards the maybe in the right hand side, that's why it is, or maybe you know that there's a water inertia issue, that's why it have the higher non-minimum phase behavior. Okay, so from the mathematical perspective, we model the like thermal for the control design for the thermal power plant. So we consider the equation 42 as a generalized third order transfer function for the thermal, and we know the PIDA parameters, you know, in equation 1 and 2, 2 or 3 we seen. So based on the P target, we form the 41, 43 equation, and 44 we just rearranging 43. Then we form the P design based on the like your order is 4. So we have the in terms of the tau and gammas, so then we can compare that, we can get the like our unknown parameter Ka, Kd, Kp, and Ki values, and we have the like our transfer of non-minimum phase hydropower plant, then we can go in the P target, P and P design, again we can compare that, and we have the here Ki 2 values, and we can how do we we get the final Ki value just like the equation 69. Okay, now so based on the parameters, based on the literature work, parameters we consider R is 2 from TG, TT, and the TP and KP values. And here we consider some lower upper bound uncertainty in the KP, KI, TD, TG, and KP, TI, TT. Okay, so based on these parameters, some initial values, we have the numerator and denominator like NS and DS. Now, so here we consider like it's CDM 2.52 as the Manabis work. So here we select the ms from the y this range, and these are the some relation with the ms or gamma 1, gamma 2, gamma 3 for the thermal power plot for the particular parameters. Okay, now you can a little bit change, then these values are worked. Okay, so you can select the ms value 1.232, then you can get the gamma such like where gamma 1 to 5 and gamma 2 2.55 and the gamma 3 1.65. So and settling time we consider here 2 seconds, then we can get the tau also. So kpi kd values, ka values we can get, and here for the hydro also we consider the parameters from literature work, and we here from like equation 76 we observed the hydropower plant is close to, they have the unstable behavior. So this is a like these values of the ms we frame from our side, so some values are available in the literature, but somehow some values not available in the literature, but we frame it in our way, and these are the consideration how much values we can consider the ms, okay, based on the time delay. So whatever the transfer function we got in the equation 76, we can convert in the first order transfer function, and just like the from the like half rule method, and we get the like t naught 1.26, so it is in range of the like last one 1.3 to 1.5. So this is like we can select the ms is just like the 18. You can see in here the like ms we have values like here this is one of the relation, and here we select the ms is 18.1628. So based on these values we can select the gammas and the kpki kd ka values. So this is a ms values we get the after the like simulation, and ms we know selected for thermal hydro as well as, or for the existing previous techniques we also compare that they have the values in the change. So lqr pid have the beyond the limit 1.222, so it is a less stable. Other like ffpid have more stable, but performance is like imc pid is okay, done it is stable. Now 1.2 it is so more stability, but there's the performance like, okay, that's why the overshoot is there, or maybe they're not take the properly the reference. Okay, now or maybe the 0. Okay, in similar way we can get the some maximum sensitivity plots also, so no issue, you can go to the from the plotting from the values. Now so here we consider the random load demand disturbance like equation 29, and here we consider the step load demand disturbance like del PD is 0.01 at the t equal to 1. So based on the these responses, step load demand and random load demand, we get our responses like frequency division is 0. Okay, yeah, at the some cycling time it get the 0, but it is settled down the, at the 0 somehow, or maybe the limit, so which is our like a desirable way. Okay, in case of the parameter considered like the plus minus 50 plus 50% deviation in the KT, KP, TP, and TG values or R also. Okay, now so these are the response we can get the better one. Like in case of the non-linear system like GRC, GDB, GRC nothing but the generation rate constant, GDB is the governor dead band. So in such a case also we can get this somehow better responses in the simulations. Okay, now for single thermal area, so these are from quantitative perspective, integral performance indices, you can get the better response. In the proposed one we get the little bit better responses as compared to the existing one. Okay, these are the lower upper and the GRC GDP conditions with random or like. So if you go with the hydro also we can get the better responses. Hydro control is a very tough in the like in the real time also, and the here also. So we, but the similar controller design is effective for the such type of the things. Now we can get the better responses now from the simulation. And so we can say that the best, or if you go with the, some renewable constant wind turbine generator we consider here like that as a disturbance we are considering this one. And based on the wind profile power deficient profile we consider like 35B. And here also we can get the similar response. We design the controller for the thermal and hydro, but in case of the renewable also we can handle it the disturbances like that. Okay, so if a disturbance there is it will go to towards the 0 deviation in the del f, and we can get the responses. Okay, now so these are the from quantitative way. So finally we can conclude that based on the like CDM based control design for the like PIDA, PID or a polycon, we can for the power converter also apply, and for the like load frequency control also we apply for hydro and thermal. We get the better response with the such type of the robust controllers. Yeah, and we have the sometimes so we can go with the IMC also. IMC internal control internal model control approach. Why internal model control approach? Because we have the controller design is the inside of the controller has the plant information or plant perspective. That's why it's called the internal control. Okay, so here we can like some worst case plant selection approach we apply here based on the Carleton's for Carleton's polynomial. Now and we have the some conditions here, but we can go with the some more to, because we can maybe have the some more things now. So here we designed our controllers, IMC controller for this particular way. PIDA controller based on the IMC for the thermal power plant. Okay, now so here KPK, KD is based on the lambda. Lambda is nothing but the design parameters in the IMC. Okay, this is IMC is nothing but the FS. It is part of the FS, like 1 upon lambda is plus 1 if you first order. Second order you can go with the higher order also. Okay, so this is IMC. Okay, you know in the figure 37 it is. So GP is part of the this controller design. That's why it's called the internal model control. Okay, now so we design this controller based on the same similar concept, maximum sensitivity concept, and we have the here relation with the lambda and the ms, and the TOD is nothing but the time delay in the now time as we design the this particular controller IMC PIDA for the time delayed load frequency control application. So here we have the how to we can get the delay margin also to like how much delay our controller is handle it. Okay, so this concept is considered under the delay margin computation. Okay, so here we get the TODM is one of the algorithm which is we discuss here, and like root tendency. So a lot of things we have, but we can just skip up. So this is the corollary one is designed us by us, and based on this we can find the time. So this is the time delay fundamental here. So generation and generation demand is just like the electricity generation, and this is our demand. System frequency 50 hertz. Now so here we send this particular 50 hertz changes we send to the controller frequency control. So there is a somehow some delay, and due to the delay that the system is less stable, or maybe the sometimes it is at the verge of the unstable condition. Okay, so how to we can handle such type of the things. So for this one, we have designed the IMC PIDA, and in case of the from the motivation perspective, the IMC PIDA is designed for the simple 10 machine 39 bus system. But if you introduce the delay in there in the system, then the controller is failed. So we have designed this controller in consideration of the time delay, and we tested our controller, and we can get the responses just like the blue in the stable way, and there is a frequency deviation is 0, or tie lines also similar way. Okay, now controller response is also required very less. Now, so we designed for the single layer and delay power system LFC here, and here we consider like e to the power minus 2ds is nothing but the delay in the signal, sending the signal to the plant, okay, from controller and two controllers also. So in such a way we get the transfer function like 116 equation, and there is a delay portion is included we have. So we design here the worst case plant condition here, and based on the worst case plant we get the some first we get the interval plant just like equation 128, and we can get the worst case plant from equation theorem 4 and 5. You can maybe, if you want to more detailed discussion, then you can go with the my one of the paper like IEEE transaction one control system technology. Then you can maybe go more study or maybe the better understanding. Now, so for multi-area system we can design, it is a similar perspective, and then we have the some like single area, and we compare our result with the FOV ID controller, and in case of the GRC GDB parameter uncertainties and all the things. So in such a case we can get our responses better way. Okay, frequency reduction control out. So control output like controller response, observe here that the IMC PIDA is required very less energy or maybe less information, less efforts to take the del F to maybe converge the del F at the towards the zero deviation. Okay, now so from the all the other perspective, all the responses we can get the similar responses. Okay, so better one as required as compared to the other existing approaches. So that's why we can say that whatever the controller you are working at, it is somehow you can go some unique things like I consider like maximum sensitivity concept, which is I got the from the reviewer side, and from the another lot of papers are people's working, but not from towards like controller design in such a way, or maybe in case of the like particularly power converter power system. Okay, so who are working in such areas and in control area or maybe power system power converter, they get the very easily some effective or unique things for their PhD work or maybe the for extra for additional research work. But you need to carry out the some things which is done by the peoples, but you can use these things, and you can do the wonders whenever your things are not working with some like tough mathematics, but you can get the some easy mathematics or some easy concept, and you can design your controller and you can get the better responses like less control energy, total variation. These are the things which is need from the control perspective. Okay, now these are the similar way we have the some parameters quantitative analysis, and somehow we observe that here some controllers are failed to control to make the frequency deviation to zero, maybe towards the limiting part. So for the concluding perspective, we got some better responses IMC beta, and we tested with the 39 bus system also. So you can check in the paper also. Okay, now for the today's problem is a cyber physical microgrid system. Okay, like a cyber attacks in the power system. Okay, so how do you can handle that? So for this one, like you heard about some in India also, a lot of cyber attacks happen in the power system in the Bombay, Karnataka, Rajasthan, and Tamil Nadu, Haryana, Rajasthan, West Bengal also. So a lot of cyber attacks and ransomware attacks, malware attacks happen on the power system. What they want? Why they are hacking the power system, or maybe they trouble us? So because they want to hack the system, and maybe they got some beneficial like from favor to some company, or maybe they got some money. So these are the challenges with the cyber attackers, or maybe those who make the trouble in our power system. Okay, now so we need some robust and resilient control system. People are working with the like designing the what was modeling the cyber attack. We have here consider some available function as a cyber attack, and we can apply in our power system and design our controller again based on some optimization approaches. And based on these things, we get our maybe responses. Somehow we handle the cyber attack response as well as the system disturbances and renewal stochastic variation of the renewable and wind. So this is one of the structure we consider here. This is our basic process, interconnection of the multiple area system. This is similar way time delay, and here we consider like whatever signal we want to share with our controller. There we have some sensitive network, so there is attacks maybe come up, and after the controller also action, there is some attacks also come. Okay, so whatever the attacks come in the whole like 2 to 3 places, we consider here one, and time delay also we consider 1 times. So based on this we can model that this thing. Here we consider cyber attack like that, NC eta CT like equation 128 and sync function like 126. So based on this we consider like this is one of the function we apply in the as an anomaly type. Okay, so if we maybe handle such type of the things, maybe our control maybe works little bit funky now. So here we consider the like design the similar way. We consider multi-area system, that's why we consider area control area ACE here, and we need to maybe AC is 0 towards our control perspective control design low. So here we consider AC just like the in the modified way. Generally people say the AC del PTI. PTI is nothing but del PTI, nothing but the tie line deviation in the tie line power, and beta is the bias frequency bias, del F is the frequency deviation, and eta C you know that cyber attack. So del AC is changed, okay, due to the attack consideration, so we change it now. So here we design the PIDA based on the optimization algorithm, and we consider the one of the objective function like the J1, J2, J3, J4, J5. Here we consider the different 5 criteria conditions and scenarios, and we can design the based on this 5 different scenarios we consider, and we can select our parameter KPK, KD, and KA. Okay, so this is we consider here 2 areas, so AC1, AC2. So here from the like previously what happened, people are selecting one of the objective like J1, J2, J3, J4, J5. We collect the all the 5 togetherly, and we can design our controller. So here is the load deviation in the profile 1, area 2, and these are the solar and the wind power deviation. And based on the controller designing KPK KD value selected from the optimization algorithm here, it is an SDO. Okay, SDO algorithm we have considered here. Okay, supply demand optimization algorithm. So we compare with the PID, this our PIDA, and we can get the less deviation in the frequencies. Okay, area 1, area 2, and the Thailand power. And in case of sensitivity like the with the plus minus 50% uncertainty in the parameters, also we can get the our better way. Okay, in as compared to PID SDO parameters. So these are the sensitivity analysis. Then so based on that all the responses, we observed that whatever the sensitive cyber attack we consider in terms of the function, but our controllers is handle the effect of this particular cyber attack as well as the renewable energy constraint and the parametric uncertainties also. Okay, so this is some things from my side as a like today discussion. If you have any question you can ask, and you can reach me at the mahendrak@nitj.ac.in, or maybe you can visit my drmahendrakumar.com for your maybe the any suggestion and any discussion regarding my work. And I'm currently working with the some cyber attacks like things which is we got the earlier our project also I discussed in initially, and I'm working with the reinforcement learning control reinforcement learning based control design load frequency control for the power system microgrid, and these things we apply in the power converters also. And so my one of the student working in the MMC modular multi-level converter, and some students are working in different areas. Okay, so this is from my side. If you have any question you can ask me. I'm open to discussion.
Yes, so audience participants, if you are having any questions, you may please ask.
Because discussion is important things during the like any presentation. I deliver the things a little bit fast maybe, and but whenever you have stuck and you have maybe the some things where you have some doubt, or maybe the application perspective, we can discuss it. Okay.
Yes, so yes, sir. I think no one is having doubts.
No
so
issue, sir. No issue. No issue.
I'll
They
give
will
you a
visit.
valuable
They
time
will
to
visit my website or something
share
like.
your precious knowledge with our participants and with us. Yeah, your lectures will be beneficial for our participants and us. So thank you so much, sir. So now I request all the audience, all the participants, we will meet tomorrow at 9 a.m. So thank you, sir. Now we can close the
Thank you,
meeting.
thank you, sir. All MNIT and other NIT partner teams for inviting me, and like we can meet maybe in
Yeah,
future.
thank you.